All right, this is a little bit of a spoiler for the next problem, but I want us to start to get the hang of what a u substitution can do for us when we were looking for an antiderivative. So remember what we learned about the chain rule. If I told you that f of x was equal to e to the cosine of x, and then I asked you to find f prime of x, well, f prime of x is going to be whatever base function this was. In this case, this is an e to the something problem. So it's going to be the same e to the something, because that's how we take the derivative of an exponential function. And then we would multiply by the derivative of the exponent. Well, the derivative of cosine x is negative sine of x. You might rewrite this, but this is not a big deal. So you might say negative sine of x times e to the cosine of x. And just notice that the result of a chain rule problem, result of taking the derivative by a chain rule, is always a product. This is the derivative of the outside with the inside the same times the derivative of the inside. So we're always going to have this multiplication here. So this is the real power of using a substitution to find an antiderivative, is if that function we're trying to find an antiderivative for is a product, if there's some kind of multiplication happening, then it's very likely that I can think of it as a result of taking a derivative using the chain rule, and then I'm going to use this use substitution to sort of undo the chain rule. So check out this next problem. So now when I want to evaluate this integral, sine of x times e to the cosine of x dx, I check. There's only one variable, so that's good. I have to think of, I notice that there's a product in my integral, sine of x times e to the cosine of x. If a substitution is going to be successful, that means that this integrand must have been the result of taking the derivative using the chain rule, which means that one of the factors in my integrand should be the function, and the other factor should be the derivative of the function. So in this case, one of these should be my u, or closely related. One of these should be a function of u, and one of these should be the derivative of u. So one way to think about it is if I thought of this, if I started separating this integrand between, like, on two sides of a multiplication dot, my choices are sine x and e to the cosine of x. So one of those is probably going to be my u, and the other then should be the derivative of u, or closely related, like within a constant of the e to the u, of du. So I'm going to use u to be cosine of x. That u, that should be like the inside when we thought of taking the derivative using the chain rule. So the derivative of the outside with the inside the same, it should be the inside. So I'm going to test this out. If I can write a new integral with this substitution that contains only one variable, then I've made a correct substitution. If using the u that you pick doesn't result in an integral that you can anti-differentiate and that only contains one variable, you got to try picking a different u. There are also some problems that cannot be evaluated using this technique, but all the ones you run into in this section in your assignments should be. So if u is cosine of x, then I need an expression for du is going to be derivative of cosine is negative sine of x dx. There's a couple ways to think about this. This is this is what method that will always work for you. And then I'll show you another way if you'd rather have a faster way. So negative sine of x. I'm trying to isolate dx. So du over the opposite of sine of x is equal to dx. Now I'm going to make my substitutions. I used to say the integral of sine of x times e to the, instead of cosine x, I'm going to write u, times dx, I said, is equal to du over negative sine of x. And now I'm going to check. If I can get all the x's to cancel out so that I only have u's left, then I can proceed. So this sine x here is going to cancel with that sine x there, but it leaves behind the negative. The only thing left in my integral is e to the u times a du. So here's my new integral. The negative, I'm just going to factor out to the front. This is the integral, the opposite of the integral of e to the u du. Can I evaluate that integral? I sure can. Well, and does that integral have only one variable? Yes. So it's going to be the opposite of the antiderivative of e to the u with respect to u is e to the u. I don't think that last part recorded. So back up here, I had the opposite of the integral of e to the u du. I checked that that's one variable, and I do in fact know an antiderivative for e to the u, which is e to the u. So my result, the opposite of e to the u plus a constant. And then at the end, my last step is to put back whatever the u was. So the opposite of e to the cosine of x plus a constant. That's my final answer. Remember, I can check the answer to any indefinite integral problem by taking the derivative of my answer and making sure I end up with whatever my original integrand was. So let's do that. The derivative with respect to x of the opposite of e to the cosine of x plus a constant is negative e to the cosine of x times the derivative of that exponent, which is the opposite of sine of x, plus the derivative of c is just going to be 0. Get me out of the way. And then watch what happens. I have this negative and this negative cancel out and leave me behind sine of x, e to the cosine of x, which is an exact match for the integrand I started with, which proves to me that that answer is the correct answer.